R3 competes in robotics competitions all over the world, and we're very excited to come back to URC for our second year. After experiencing the terrain and traction conditions in Utah, we went back to the drawing board, focusing on higher speed, lower weight, and increased controllability for all our subsystems.
Our chassis and drivetrain team has worked hard this year to reduce the weight of the rover, take advantage of new manufacturing methods, and improve terrain traversal. Last year's rover proved to be critically close to the weight limit, so this year a smaller rover was designed to drastically reduce the weight of suspension components. To further reduce weight, the core loads of the rover, such as the robotic arm and the batteries, have been moved much closer to the center of the chassis, and a carbon fiber outer shell is being manufactured to house the electronics in an ultra-lightweight way. To improve our terrain traversal, the suspension geometry has been modified to make obstacle clearance easier, and several prototypes of wheel treads have been tried to greatly increase the amount of traction the rover has. For the suspension, carbon fiber tubes have largely replaced welded aluminum, and carbon fiber embedded 3D printing has been used to produce the joints between them.
The ARM team this year is taking a new approach to design, focusing on simplicity for the least possible weight. We have built a SCARA-style arm instead of the traditional 5 or 6 degree of freedom robotic arm. The SCARA design offers more rigidity and less backlash. It also features a Z-axis of vertical movement that helps our auger for the science task for fast and precise drilling with over 35 pounds of force. Two smaller arm segments move to cover a horizontal flat plane just large enough to type on a keyboard. With the use of a camera mounted inside of our 4-finger gripper, this makes it simple for drivers to navigate and interact with unfamiliar objects. This setup simplifies programming, and by applying Cartesian-based inverse kinematics, we have 100% automated the on-rover science task, as well as other simple parking and generic movements.
This year, the controls team designed a highly extensible and reliable control system to focus on superior control experience for all teleoperated systems. We've implemented a new control architecture to better utilize ROS control, allowing us to have a modular control system at every level, including hardware and software. ROS control allows us to accurately simulate all of the systems on the rover in real time, letting us quickly prototype and iterate all of our high-level control algorithms without the cost of damaging the rover. Due to the nature of the URC competition, our new rover utilizes 900 MHz for its capabilities in non-line-of-sight situations. All critical communications, including teleoperated commands and primary camera feeds, are operating in this frequency. We pair this with 2.4 GHz for all auxiliary camera views and non-crucial data. For the autonomous task, we use a combination of real-time appearance-based SLAM and move-based for autonomous path planning. Our system primarily uses input from our custom stereo cameras to do its own path planning, but also allows for operators to do high-level planning and general path indication. In addition, we have designed redundant autonomous systems utilizing GPS and IMU data should the primary system fail.
For the science task, we developed an arm attachment and automated console capable of housing 15 sensors that simultaneously collect and send data back to the base station. This is a huge improvement from last year when we only had 3 sensors. This year, we're monitoring soil for hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, and radiation levels. Additionally, we're measuring electrical conductivity, redox potential, dust particle density, pH, temperature, humidity, wind velocity, pressure, and altitude. Our biological tests are all simultaneously performed at the command station. We have expanded our assay to include DNA, RNA, and protein extractions. Our novel shotgun-like molecular biology protocols use affinity differentials to sequentially hone into our macromolecules of interest. This way, we can use spectrophotometry to quantify each step and calculate the UVC 260-80 ratios. Our tests fit within the safe 10-minute mark, leaving enough time for replications. For the geology task, we've developed image analysis algorithms using OpenCV capable of differentiating soil layers and soil samples under a microscope. We're confident that using our physical, chemical, and biological tests will allow us to give a strong assessment of extraterrestrial life on Mars.
We are extremely confident that we will perform well at URC 18. Our focus on reliability and weight has yielded a robot that is over 12 kilos underweight with our heavier testing frame. In the coming weeks, the team will be finishing our carbon fiber shell and our gripper, after which we will begin a rigorous testing plan. Good luck, and we hope to see you in Utah.